right, so let's talk about alkenes. When we talk about alkenes, please just remember that we are talking about hydrocarbons that have a double bond. That is what we call a double bond between carbon atoms. Please don't say that the carbon bond between hydrogen and carbon. No, it has to be between carbon and carbon. So this basically becomes the identifying feature about the alkenes. So they determine the number of their chemical reactions. So what we are going to look at the different alkenes, how we name them. We'll also look at how do we consider the position of the double bond in naming them. We should also look at that. We'll look at how we can prepare ethene in the lab. Okay. Remember that ethene is basically the starting compound for alkenes. Okay. In alkanes, we started with what we call methane. Okay, this actually is their compound number 1, and it is the one with single hydrogen, carbon atom with 4 hydrogen atoms. With ethene, since the double bond has to be there, you are starting with having at least 2 carbon atoms. So that's why we are focusing on ethene preparation, the uses of ethene, and also the chemical properties of ethene. So, like I said, double bond has to be there. The presence of the double bond makes them what you call unsaturated. Make them unsaturated. The presence of the double bond makes them unsaturated, and they have a general formula CnH2n. So if that n is equal to this n has to be more than 2. This is the emphasis here. Can be 2 or more than 2. It cannot be less than 2. That's the point here. So if this n is 3, let's see what would be. It means that with the Cn, with the CnH2n, and if n is equal to 3, it means that you have C3 and then H6. So what's the structure of this? It is basically this, but we can still draw that. We can say you have 3 carbon atoms, but out of the 3 carbon atoms, at least there should be a double bond somewhere, whether here or there. And then we can add our hydrogen atoms. Are we good to go? Okay, so they have to be 6. Remember, the reason as to why I've drawn that is because for each carbon atom there should be at least 4 covalent bonds. Okay, so this is 1, 2, 3, 4. This is 1 for this carbon now, carbon number 2, 1, 2, 3, 4. Carbon number 3, 1, 2, 3, 4. So each one at least has 4 bonds. That's the rule, okay, for these compounds. That means that we can write this as C. The first carbon has 2. The next carbon has 1. The third carbon has 3. Yes. So what is the name of this? with the 3, that is propene. That is propene. That is the alkene there. Okay? Yes. So nomenclature, like we have just seen, that propene. That is that. So 3 carbon atoms, and then the first one, of course, has to be one which has 2 carbon atoms, and then the 4 to make sure that everything is covered, every carbon atom is covered. And then this but means 4, but here we are having an issue of isomers, where we said we have the same molecular formula but different structure formulae or formulas. Okay, and then the other issue that you also have to think about is the fact that in naming them, which we say that is nomenclature, one of the identifying things is to have that as the suffix. Okay, it ends with that. If you see something ending with that, then it is an alkene. Okay, so the usual rules of nomenclature follow that we talked about in lecture number 1. We also looked at that in session number 2, I think, yes. And then now the same rule apply in naming all these organic or hydrocarbons. So alkenes generally are actually reactive. Okay, that's one of the things that you really need to note. Compared to alkanes, So the first 3 are gases. Okay, this is the other name for ethylene. Please don't, ethylene is the same name, has the same name for ethylene, right? It's the same as ethylene. 3, 4 carbon atoms. So the first 3 members of the alkenes are gases. From number 4, from alkenes with the carbon atom 5 to carbon atoms 15 are actually liquids. And then more than, if you have an ethene with more than 15 carbon atoms, then definitely that one is going to be a solid. Like all organic compounds, they are insoluble in water. Okay, they are insoluble in water, but soluble in what we call organic solvents. Okay, because this actually, the alkenes are insoluble because of their non-polar nature. So the organic solvents that alkenes can dissolve in, ethanol, for example, is one of those that it can dissolve in. They have distinct kinds of smell, but these vary because we have different alkenes that we have depending on the number of carbon atoms that they have. So they burn in presence of oxygen, of course, to produce different products. We shall see that where carbon dioxide is produced and water. But basically, if you have limited oxygen, that is when you produce that sweet luminous flame. Okay, that is when you produce that. They are less volatile. They have higher boiling points and melting points compared to the alkanes. Okay, compared to the alkanes, and this is because the alkanes have smaller molecular weight compared. No, let me repeat that point. They have the alkenes have higher boiling and melting points compared to alkanes of similar molecular weight. So if you have alkane of, let us say, alkane of 3 carbon atoms, and then you bring an alkene of 3 carbon atoms, the alkene of 3 carbon atoms will be having a higher boiling and melting point compared to the alkane. That's the point that we have there. So they exhibit what is called isomerism, and perhaps we're introducing this concept for the first time. In my earlier explanation, the emphasis was on the position of the methyl group, the position of the atoms. But one of the key things that can result into isomerism can be the branching, which we already explained, the point at which the branching happens, the number of carbon atoms at which branching has happened. They may differ when you have a compound of the same molecular formula. But the other concept that is also very important that we are looking at now is what you call positional isomerism. In this case, we are referring to the position of the functional group, and in alkenes, the functional group is basically the double bond, because the double bond is one which will influence the characteristics of the alkenes. Okay, so the position of the double bond is the one that can bring about what we call positional isomerism. So now let's check an example using butene. So butene has 2 isomers. That means that the position of the double bond can be different, but it will still remain butene. Okay, that is what we mean by isomerism. So butene has 4 carbon atoms. So we can start with that. 4 carbon atoms. There should be a double bond somewhere. Okay? So after putting the double bond, we should make sure that at least each carbon has 4 bonds. Okay? And in this case, do we have 4 bonds in this, and that, and that? The answer is yes. Now, the next thing to do is to confirm that indeed we have 8 hydrogen atoms, just like what we have here, because butene has 8 hydrogen atoms. Do we have the 8? This is 1, 2, 3, 4, 5, 6, 7, 8. That is true. So that means that this is what we have really represented very well. So far so good, right? Now, where is the position of the double bond? It's at position 1. So this becomes it here. But to mean 4 carbon atoms, the double bonds at carbon atom 1 here. But we can still have the same this, the same that, but this time the double bond is in the middle at carbon number 2. So you have C, 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 and C. But the double bond is now here. So we also make sure that each one has 4. Each one has 4. No. This one is not there. Like that. Okay? So position number 2. That is what we have here. But2 in. Okay? So how do we prepare ethene in the lab? We basically dehydrate alcohol. Dehydration is removal of water, right? So you heat ethanol in presence of sulfuric acid at temperatures of this, you will get ethene. Okay, you'll get ethene, then of course have steam. The sodium hydroxide here is used to absorb any acidic impurities that can be in the ethene that you have. So it is very possible that this connection can go direct here. But if you don't want the impurities, make sure you connect to this sodium hydroxide solution in that wash bottle, right? So you get small amount of ethanol in a round bottom flask, and then you add the concentrated sulfuric acid dropwise while cooling the flask, because the reaction actually gives heat also. So that is why the cooling of the flask has to happen using a water tap. Okay, so water can be flowing here from a tap, right, to cool this, because the reaction is actually also releasing heat. Okay, so you heat, the temperature has to be high, 170 to 180 there. Okay, and then the gas will be collected over water, okay, by what you call downward displacement of water. Okay, passing it in a wash bottle of sodium hydroxide removes any acidic impurities. You have seen that. But also, the process of cracking, actually, for example, at industrial level, can be used to produce this ethene. But also other products can actually be produced. So what is this cracking? The process of breaking down these long hydrocarbon chains into smaller molecules. And these smaller molecules are the ones that can be used to make different products. And most of these products are used in the petroleum industry. So these shorter products can include things like kerosene, diesel, and also, by the way, this can also produce some alkenes. Okay, so we can also talk about alkenes being produced. Okay, so if we will ask you about the definition of cracking, we are saying that it is the process of breaking down large hydrocarbons that are formed in crude oil to produce smaller useful molecules such as the alkenes and some alkanes. That is where we get petrol, gasoline, diesel, and some alkenes. So this is basically a simple representation of what really happens. You have larger molecules that you feed into the machine, and then you have smaller molecules at the end. So the processes can be of two types. Cracking can be of two types. It can be achieved using a lot of heat. That's what we call thermal. Thermal meaning heat. So you subject these large hydrocarbons to a lot of heat of about 700 and above to break these bonds to form the small hydrocarbons. And then also you can have what you call catalytic breakdown. Here, catalytic cracking is about using a catalyst. With this, you basically don't need to have higher temperatures. Since you have a catalyst, you can use around 450 to 500